like, you know, one of the hard things when you're talking about Bitcoin is that there's so many different aspects to it. And if you just focus on kind of one aspect, it doesn't give justice to the whole. And it's always hard to figure out which aspect you kind of talk about. And so, you know, you kind of, like what I was going for in this tutorial is like, you kind of encounter this when you try to explain Bitcoin to your friends. You know, is it hard money? Is it a open source project? Is it a payment system? Is it a ledger? Is it a P2P file sharing network? You know, is it programmable money? Is that you know, like, what do you start with when you just describe it? And so, you know, I think we've probably all experienced this, and it's similar when you're trying to teach people about how it works. Is like, you know, what I'm trying to do in this class is it an internet protocol, you know, on top of TCP/IP? That's one way to look at it. Is it a smart contracting system? Is it a quote unquote blockchain? Is it a specific set of like transaction abstractions? Like what technical aspect do you start with, and where do you go from there? And so with this class, we're going to start with that first one, an internet protocol atop TCP/IP. We're just going to start with the network programming. We're going to jump into the kind of the peer-to-peer network and start trying to figure out how to connect to our peers. You know, one of the 10,000 or so peers, you know, also known as like full nodes or SPV clients or any of the clients that connect to the Bitcoin network. And we're gonna join and try to kind of learn to participate, learn the language that these peers speak. We're gonna learn what kind of messages they send around. We're gonna learn how to interpret these messages and how to kind of reply and participate. And eventually, the goal is to be able to do initial block download. So actually download the blockchain, verify or validate, you know, every block in the blockchain, and get to a point where we can actually, you know, say whether a given transaction that's happening now is valid or not. And so I don't know if we'll actually get there. I think we could probably get there if we made a simpler environment in like a reg test. It's a little testing tool for Bitcoin. Or it'll be kind of hard to parse 200 gigabytes worth of blocks in Python because it might be a little slow for that. But you know, maybe if we just, you know, can do initial block download for the year of 2009 or something, like that would be pretty cool. And I think we'd be really happy. And I think we'd all understand how Bitcoin works a lot better. And, you know, it'd give us a point to kind of expand our knowledge in the future. So, so yeah, any questions kind of about that, about how we're going to go about things here?
Makes sense to me.
No.
Cool. So the first thing I want you guys to do is like, let's go to this, let's actually go and try to connect to a Bitcoin peer. So yeah, let's open this link here. And let's go to, so it's just a list of a bunch of Bitcoin nodes. And so if you scroll down, you can see, you know, these are just, you know, this has 10,000, about 10,000 nodes that it's found. And let's go and actually copy one. So I'm going to go here. I'm going to just copy this node. So it's an IPv4 IP address, and it's a colon and a port number. And so this is just how the IP system works. You know, every kind of computer that communicates over the internet uses these addresses to kind of address each other. And so I'm just going to choose one at random. I mean, it's sort of funny. This one's running in Amazon EC2 probably, and you know, it's kind of interesting. Actually, a lot of these, if you look over here, quite a few of these are running in cloud services, which is a little alarming. But you know, so let's just, you can choose any one. And so I just grabbed one, and I'm going to just paste it in here in this next cell. And so what we want here is we want to take the IP part of it and stick that into this peer IP address. And let's grab this port number and let's stick that in here. So we're just going to grab so now we have some variables for IP and port. And I'll give you guys a second to do that.
Oh, okay, I'm with you.
Got it managed? Okay, cool. So now let's open a raw socket. So like a socket is kind of a method of kind of communicating between two, I guess you call them like hosts or even processes between the same host, you know, one computer. And I don't know if it actually I think it exists on Windows. I mean, I think we have sockets on Windows, but they're kind of like files, and they allow you to basically communicate across the network just like you were communicating with like another file or something on your computer. And so you connect to it, and then you can read from it, which is this recv command. And we're just going to pass like an arbitrary number of bytes that's going to be bigger than any message we could get. And so, yeah, create the socket, connect to it, and let's try to read from it. And if we execute this cell, oops, so in Jupyter Notebook, you have to execute every cell. So I had to execute that one, go and execute here. And so you'll notice, previously, every time we executed a cell, we haven't seen many, but there's a number here. This is like the order you executed it. And this means it's done when there's a number. If there's no number, it means it hasn't been executed yet. And so this one is different. It's a star. What does a star mean? A star means that it's still executing. It hasn't finished yet. And so the reason for that is that we're trying to read from this socket, and our peer. So we successfully managed to connect to them, but our peer is not sending us anything to read. Somehow we haven't like introduced ourselves correctly, and our peer is not willing to talk to us. And so if you just hit I twice, you might have to hit escape first. I just says interrupt. It just interrupts the execution of the current cell. And you'll see here in the stack trace here, it's stuck on this receive. So it's just like stuck there. Why is it so slow? And so, or why is it's sitting there? And the answer is you'll see in this, if you kind of read this whole thing. If you look at this link, and this website is the kind of the best, in my opinion, the best kind of wiki for information on the Bitcoin protocol. They have a lot of really great resources. And so this is kind of just like an ASCII diagram of how the handshake works. So this is how you actually join the Bitcoin network. Every time any peer joins the Bitcoin network, you have to do what this little thing describes. So if you have a Bitcoin full node, you got to do this. If you want to be a miner and you want to submit blocks to the blockchain or to the network, you're going to need to have done this so that your peers will listen to your messages. And so how this works is you have two peers. One of them is you, local, meaning you. So L is me. And then remote is like, you can think of it as like away from you. Remote is them. And so the first thing you do in this handshake is you send a version message. The person who initiates the connection, the local peer, sends a version message. And so you'll see right away, like, no wonder we failed. We just connected and started waiting for a response. We didn't, no version. We didn't send a version message. And so, of course, our peer is going to ignore us because we violated the protocol. And so, so there you go. This is what we got to do. And then, so what do you do next? Your peer will send their version message. And then they'll also send a var_ac message, meaning like, hey, I got your version message. Var_ac is just like acknowledge, right? And then so lastly, once you get their version message, you send a var_ac. And so at this point, both sides know, and this thing is like, you have different versions of the software. So like a proper full node will keep track of what version of the peer you're talking to is. And they'll only send messages that the peer will know about. And so this is something that's kind of a detail that we're not going to be concerned with, but at this point. But after this, you're like a full member of the Bitcoin network, and this is really a profound thing, People think like Blockstream or something like that is kind of like, they're censoring people and they're controlling the network and everything. But on an actual technical level, a Blockstream node and your node are exactly the same. Like, they do this handshake and they are equal peers on this network. There's no special privileges a Blockstream Bitcoin node has. It's running the same software as you, and there's no API key. You just get right in the door if you can follow the rules. And like, this is really profound. Like I worked at a traditional financial technology startup before a couple years ago. And I mean, it's night and day. You couldn't get into any of these networks without like 6 months of business development in order to get in the door. And so this is like, I mean, this is really mind blowing and shocking that you can do this. And I think, one of the goals of this class is to kind of drill in this idea that, this is, permissionless money means you can actually learn to code and, jump in here and do something, which is really amazing. And so yeah, this is basically what we're going to try. The first 3 lessons of this course are going to be about how to do this from scratch. And that's, we're going to do it by hand. We're not going to use any other third-party libraries. We're just going to be reading and constructing raw messages, raw bytes. And so it's kind of really, bare metal, close to the, kind of programming. So yeah, that's kind of the introduction to the class is like, that's, as soon as we can figure out how to, send version sent, as soon as we can do this, if we can do these 4 things, then at this point our code will be like a full, down here we can do whatever we want. We're full members of the Bitcoin network, and that's really great. So that's this kind of intro to the course is like, this is what we're going to spend 3 lessons trying to do. And then after that, we're going to proceed. We're going to write a little crawler that crawls across the network and kind of figures out what version of software everyone's running. And then we're going to try to do initial block download. So yeah, I'll stop there. And before I show you how to do that, kind of any questions about this version handshake thing I showed you or anything like that, what the ports mean? Any questions about that?
Well, Justin, I'll go ahead.
I was going to say, it makes total sense to me.
Okay.
John, you're going to say something?
Yeah, well, after going through this, I realized I had made a rookie mistake setting up a full node because I tried to connect and got into the whole port rabbit hole, and now I'd like to connect to my node. And I don't know if you guys did that when you did this before, if you talked about that, just, while doing this exercise, connecting to your own node.
I actually haven't done that yet. So I just set up a node on a little mini computer here, and I just actually, I was just setting it up recently. Like I've had nodes in like AWS before, but I'm trying to actually run one here. And I actually need to check on it. I just had it like resync the chain state directory. Like I transferred all the blocks from my computer, my laptop, onto the thing, and now it needs to, I don't know what it's doing right now, but so maybe in a day I can try that.
Yeah, well, I looked, and then I looked up, that made me realize that there's not just one type of node. And so I guess technically mine was a selfish node that had a copy of the blockchain, is not pruned, but was not broadcasting. And then it looks like you can specify how many peers you can connect with, but you can actually do a lot of data transfer if you want to, like in the gigabytes.
Oh yeah.
Yeah.
It gets pretty huge. Yeah. I mean, especially if somebody connects to you and tries to do initial block download with you as like a peer, like you can easily send gigabytes of stuff to them because they need to download 200 gigabytes worth of data. Right.
Right. Yeah. I mean, and that made me realize too, how I'm sure that there's not very, like there's different, it's like an onion, there's nodes, and then you could go all the way down to the full nodes that are connecting with unlimited peers. I'm just curious what the number what the number of nodes that are willing to do unlimited data transfer is, because I have a cap with Comcast, and so I want to do some, but
Yeah.
I saw like over 100 gigabytes in some cases. I guess that's just one blockchain, so that's
Yeah, literally.
I
If
mean
somebody just
I guess it literally could be terabytes, but
yeah.
yeah. It's just that was really interesting to me. So
Yeah.
sorry for going off on.
No, I mean one thing that would be cool is like, you could kind of go around if you wanted to test this, you could get a understanding of what the network is, and you could just start connecting to people and just see how much they'll let you download, right? Like,
right.
You could write a script that pretends to be doing initial block download and just sucks down the entire, see if they will give you the entire 200 gigabyte chain, and maybe they'll cut you off. Maybe you start getting rate limited, but like, you could actually write a Python script, and by the end of the class, I think you'd know how. You could write a Python script where you like empirically kind of test this with various people,
wow, that would be, I guess, that could be like a deep dive blog article.
Yeah, totally.
Yeah, I know that only appeals to a certain number of people, but
no, I think you get all these questions about kind of how it works in practice. And I think when you kind of explore these little things, then it's the only way to really understand how the network kind of works, like on a technical level, of course.
Is that an attack vector? I'm not really sure how that would affect Bitcoin security.
Who knows? Yeah, it's one of the many questions, but I'll keep that in mind as we go. Maybe we could try something like that. If you tell me what the port and IP of your full node is, you're going to be in trouble coming up. Take gigabytes. All right, well, let's go to this next one. So all we do here is I just give you this magical string. It's actually like a byte string. When you prefix the string with a B, it's like it's just like it's a different kind of encoding of the string, and that's kind of all you need to know. There's just kind of a string, and this one is basically just raw bytes, and the regular string in Python, you can put like Chinese characters like that in there. It's full Unicode, right? So it supports Unicode supports or like UTF. I think UTF-8 is basically Unicode. That's like, tens of thousands of different, I think 65,000 different characters you can fit in there. It's just insane how many different types of characters there are. So that's a string, and byte string is a little less, you can only, you basically this is what you'd kind of encode those things down to when you encode a string. And bytes are what you send over the network when you do raw socket connections. And so that's what we're going to do. We're going to just create this version message, and you can look into a little bit. Like, we're going to learn this number. This number is the prefix of every Bitcoin message. Every message starts with this up to the version. And then the second part of every message, you get 12 bytes the version, they're the message name, the name of the message, and then write padding with empty bytes. And so actually it's more like here. And so that's, you can kind of see the message, and then afterwards it basically becomes like gobbledygook. You don't really know what's going on. And then at the very end, here's some cool software. It's like, oh, I can understand that. That's just our user agent. I just wrote that. And so and this is kind of interesting. It's like this is like the key to get into the Bitcoin network. And later on, in lesson 3, we'll learn actually how to construct this. And so we do the same thing we did. Create a socket.
That was my next question.
Huh? Yeah. We create a socket, we connect, and here's receive and print, the same thing. But now we just send version, socket.send, right? And so, and that's all we do. We send them these magic bytes to our peer who we've connected with. And if you run this, magically, you get a response. And see how there's no longer a star here? You're no longer stuck spinning. You're no longer stuck blocked on waiting for your peer to respond to you. And so this is, pretty cool. It's once again, an equal opportunity peer-to-peer network. You speak the language and you're in, no discrimination here.
Justin, why does the network require that version key? is it just about making sure everybody's synced, or like, is there like, how hard is it to generate a key or to get the key?
Yeah, so it's actually not a secret key. It's not like the point of it is more that, like, you know, other things flying around on the internet don't get confused for Bitcoin messages, and kind of it's just like weed out the noise. Like there's no, it's not really a security thing. It's just like a logistical thing. Like let's you know,
Okay,
for example,
that was really the question. If it was more like logistical or a security
yeah,
thing.
so a Litecoin transaction would have a different key here. And, you know, especially at the beginning, you know, Litecoin was basically Bitcoin. Like it was the same thing. And actually, you know, someone told me that, you know, when Charlie Lee created Litecoin, it took him like two hours or something. Took him 2 hours to build Litecoin.
Wow, it took 2 hours to make 50 million.
Yeah,
however much you sold for.
It's insane.
Wow, that's a really good ROI.
Yeah, so but that's all he had to do was, you know, he just had to kind of run through the source code and like change, you know, he had to change this variable. And if you go to this
I feel like 50 million's conservative.
Yeah, so
what he sold out for.
Version. Or no, we want magic. Message structure, network magic. Okay, so here has testnet and Namecoin, I guess, Namecoin. But, you know, so you just want to be able to like differentiate a testnet message from a mainnet message, right? You know, you don't want your testnet coins. You want to be able to say, hey, this is not a mainnet message. I don't want, you know, to spend my coins. I want to test that I will correctly spend them when I do try to spend them. So so that's kind of the point there. And yeah, so that's, I mean, pretty simply, that's how it works. So any more questions, or ready to move on?
That makes sense to me.
Cool. Yeah, so so that's great. Now we're at this point. Hey, so let me see what we're gonna do next. Yeah, so so we got this right, and this looks like gibberish. You can see they have version also, right? And then five empty bytes, and they also have the same starting string. And they also have here, it says Satoshi 0.16.0, where ours said some cool software. And so, you know, you can see that the structure looks pretty similar. It's maybe of a similar length. But other than that, it's really hard to tell what's going on. And so that's kind of the, this is kind of one of the core skills required to do like, you know, write Bitcoin software, is you have to be able to encode and decode messages like to and from bytes to these bytes. You know, so each one of these has this is like a delimiter, right? This basically says this is a bunch of bytes, right? And the first one is like a 0. This is a number between 0 and F. And so this is basically the number between 0 and F in hexadecimal is 16. And so you get 2 of those. Each one of them is a number from 0 to 16. And 16 times 16 is 256. And let me just like, so like, just this is like a little, what is a byte? So 16 times 16 is 256. So in any one of these, there's 256 different options. And that's basically the same as, a byte. 256 different things. So a byte is 8 bits, and a bit is just either 1 or 0. It's just 2 things. So if you get 8 bits, the number of possibilities is 2 to the 8. And so, you know, this here, every one of these, it's just a different way to represent something like this. Is there 8 of them there? Yeah. So like, you know, for example, 0F. You know, that would be like, oh God, I'm not going to be able to do this very well. So that'd be like 15. So that would be something like this. You know, something like this. Maybe. So that's 1, 2, so that's 3, 7, 8, 15. I think that's how you write 15 in binary. So, you know, that's just a little overview. Like, this is the binary representation of the number 15, I think. Let's see. Yeah, and so that's the binary representation of the number 15, and 0x. This is how you'd write it in hexadecimal. And so that's kind of, you know, if you don't totally understand that, this is something we're going to be going over a lot, is just like the different kind of ways you can represent information. And in these byte strings, it's like these bytes, these values from 0 to 256. And then what we do is when we read these bytes, we learn to interpret them as different types of data, right? So like, if you hit this link here to the protocol documentation, this is the documentation to the version message. Did you see that? It's just in this next little thing. The protocol document tells us what the version message contains. So if we go there, you'll kind of see this is what is in the version message, right? You have, and this is why it's useful, right? This version number will tell you the different, basically what the other node can do. Services is like, you know, what kind of things, basically what new BIP features they have enabled. You know, and so that selfish node you were talking about, John, you know, you probably had a lot of these things turned off. You know, you were telling people, you know, fuck off. I'm not going to play with you guys, basically. And so if you look at the next link in this thing where it says the message structure, if you hit that one, this basically gives us what the structure will look like for the overall message. For every message, we'll kind of adhere to this. And you can kind of see, okay, here, 4 bytes, magic, right? And the magic is this. Well, that looks pretty familiar, right? It starts with D9, ends with F9. This one starts with, well, there's D9 on the back and F9 in the front. So it's like, it's probably the same value. It's just kind of backwards. So that's interesting. And then there's the command, right? 12 bytes. So there's the start of a command, and then, you know, some zeros after it. That could be padding. And so that's kind of the command. And you sort of see this you can kind of see just from this first message that, you know, this is structured, or could be structured in this way, this message structure way. And so if you don't understand some of this stuff, like this is a deep rabbit hole, and we're going to spend a lot of time going very, very in depth on how to interpret these. And this explanation is just like, you know, what the road looks like. You know, it's just kind of, you know, there's this kind of spec for how the messages are organized, and how each kind of command and or payload from the messages is organized. And we're going to be kind of basically translating this entire page into Python code along the way to our initial block downloader. So yeah. Next, we're going to do a little bit of that, but any questions on that kind of introduction?
Oh, good.
Cool.
No, I mean, I think what's great about that is I feel like I can look at all of those characters and actually make something out of that.
Sure, exactly. And so, yeah, so when we go back to the message structure table, you know, we see there are 5 things, right? And so what we're going to do is I'm going to take these version bytes. These are the bytes that, you know, when I wrote this, some peer gave me, right? Just like the one we sent, and just like the one we just received. And this is a little code that will actually take it apart and read a certain number of bytes at a time, and just sort of print them out. So if we run this, you'll see the first thing it says, okay, 4 magic bytes, and here are the same 4 magic bytes we've seen. Okay. And here are the 12 command bytes. And there you go, version, and then some empty stuff after it. 4 length bytes. Okay, length is, there's an F, and then there's some empty bytes. Okay, that's kind of weird. But checksum bytes is some bytes, okay? And then payload bytes. This is what is left. So that's kind of interesting. You know, we can start to, we're slowly kind of peeling the onion away. And if we look at how the code works, it's pretty simple. It just, if you've ever worked with array indexes, right? Like, you know, it's just like this. this is going to take the fifth element in the range from 0 to 10. So, right, 0, 1, 2, 3, 4, 5, and it'll just print 5. So it's going to give us the fifth one, right? Pretty straightforward. This is the same idea, right? Like, if we want to start with the fifth element and go to the end of the list, you do that. This just says, like, go from the beginning to the end. If you want to go up to the fifth element, you do this. And so this is all we're doing here is we're just using array indexes to kind of read a certain number of bytes at a time. And fair warning, this is really ugly code, right? You don't want to write code that has a bunch of plus signs, and like, this is really ugly and it's really confusing, but it does work. And later I'll show you a simpler way. And where do we get the numbers from? Well, we read the first 4 bytes because the message structure says that magic is 4 bytes, right? And then it's 12, 4, and 4. And if you look over here, that's how we're doing it, right? We read 4 bytes, right? And then we start at the 4th byte, and we read 12 more, 4 plus 12. Then we start at the 6th byte, 4 plus 12, and read 4 after that. And so that's kind of how we're doing it, is we're starting with, we're doing slicing, it's called, We're taking a slice of the array, or it's actually not an array, it's an iterable. In Python, there's many different things that you can do this slicing with, and a byte string is one of them. And so this is just a simple, quick and dirty way to kind of take this message apart and kind of spit out what's inside. And yeah, any questions about that?
Are we just, are we doing what we just did just to help us understand that, like, does this have anything, I was trying to get at if this was getting towards doing our own implementation, or is this just us understanding?
It's the simplest version. Like, so I mean, we still don't know. Like, inside this payload, these payload bytes, the version number is hidden in there. This. In the end, we'll be able to pull out this addresses, user agents, nonces, services. This is all the different things that the node can do. In the end, we'll have to be able to pull all this information is encoded in this little byte string. And you can see part of it. You can see the user agent right here. And so this is just the first step. It's just demonstrating, hey, this is how you at least slice the different parts, but we don't know how to interpret them yet. If you look closely, I actually did interpret one of them. I did interpret payload length. And that was this int.from bytes of payload length bytes, and then this little, what the hell is little? But if you did that, all of a sudden, if we run it again, it'll print out 102. And, or actually, we already had it here. So it's kind of what, the first thing you'll notice is that with every one of these, with the first 4 bytes, next 12, the next 4, with each one of these, we already knew how many bytes to go. But at the end here, we actually jump by this payload length, which is something we calculated dynamically based on the beginning of the message, or based on the third part of the message. So that's kind of cool. So yeah, to answer your question, it's the first step in sort of decoding this.
Got it.
Yeah. And so here you go. Yeah, like version, first 4. Command, next 12. Length, next 4. Checksum, next 4. Payload, next length bytes, where length is this third thing we calculated. And so that's pretty cool. Like, anytime you're like, this is happening probably thousands of times per second across the world, way more than that, actually. Every message that's sent across the Bitcoin network, and every transaction that is put onto the Bitcoin network has to be synced across all 10,000 peers, So, and that's not even including the block that it goes into, and the block that is in every single time someone downloads that block, an initial block downloads. Like, every transaction you've ever done is getting packaged up into these messages many thousands of times. So that kind of ready to move on from that? Make sense? Mm-hmm. Yeah. So a simpler way to do it, like what we'd really want to be able to do is basically call socket.receive. Just like, remember how we did up here? we called socket.receive, and we're able to print out the response. That's basically what we want to do. Is we want to be able to call socket.receive and kind of as we go interpret what it gives us, you know. And instead of like, and so the reason why you want that is that this payload length, right? The way you get the payload is variable. So it's like if you do this with just a fixed number, you're never going to be able to kind of nail the beginning and end of every message. If you always read a fixed number, like all of a sudden, you know, this is message A and this is message B, and you're going to like read half of message A, and then the next time you start reading, you're going to read the other half of it with some of message B, and it gets all mashed up and your program can't work. You have to be able to like read message A, stop, and then, you know, read message B, stop. You have to be able to stop on a dime when you're done reading the message. And so that's why this is bad. This is never going to work. And this is good because we can read a couple bytes at a time. And so if we could just go, you know, as we go, say, you know, sock.receive of a few bytes, that would be great. And so what this is here is this is just I made a little like a class called fake socket. It just kind of hacks together something that behaves just like a socket. And you don't have to understand how this works, but it basically pretends to be a socket. And so if you execute that, you'll see this new cell of code. Looks a lot like the old one, right? It's structured the same, print statement's the same. But here, instead of having all these indexes, we just sock.receive of that many bytes. And so all of a sudden, that's way better, isn't it? Like, it's way easier to read, and it also gets rid of the problem of doing sock.receive of a fixed number, right? At the very end, we can just say, hey, I want to get the remaining bytes in this message, and then I'm done. And so this will work a lot better. It'll be able to stop when you need it to. And so if you print this, you'll see it printed out exactly the same thing. And so we're kind of rolling here. We figured out how to read bytes from a socket and stop exactly when we need to. And we're going to be doing a lot of that. So if you don't like this, you might as well, you know, we're going to be doing a lot of this. So any questions about that?
Yes, I was looking at the code for that yesterday. So that it all kind of traces back to the read function from the IO library. Is that right?
Yep.
That's kind of, yeah. And so how that works is it's basically, so we're looking at magic bytes and then command bytes. So it reads the first 4. Yeah. And with command bytes, it knows, okay, so you got up to 4, let's read the next 12. That's kind of basically how it's working.
Yeah, so it's like if my forearm here is like the message, right? You start here, and or I guess you will start from the left so you guys, yeah. So you start here, right? And then you read the first 4, and it sort of like remembers where it stopped, right? I stopped here, right? And then so when I call read again, it doesn't start here, it starts here because this is where it stopped. And so when you're reading out of a socket, it's like once you read these, you don't really need them again. Like the understanding is if you needed them, you saved them in your program. And so we're just going to start here and then read up to here, which is the end of the command, and you know, so on and so on. And so that's all it does is inside it just keeps track of where it stopped.
That's the whole point part of it. Okay, yeah, just trying to understand as we go.
Yeah,
know, like
exactly.
as well as the the Bitcoin stuff. So that's cool. No, thanks.
Yeah, so it's and you know, stuff like this is like when you learn more programming, one of the things you get really good at is making like tiny little, so you say like, oh, I need to test some code. Well, I don't want to create a whole socket because the socket is actually a pain in the ass. Like, how do you put in the bytes you want? You know, how do you know, in the extreme, the stupid thing to do would go to be set up a whole full node, which you could, you know, on that side, tell what you want to come out. Or you could just do this. You could just make a little test, a little helper that pretends it's a socket as far as your program knows, you know, and behaves like we want it to. So yeah, I think it's a cool little kind of demonstration of that idea. And the one thing here is that you have this skip bytes thing. Is like in the future this is just a little helper. Like if you want to create a version socket and like let's say start at, you know, skip the magic part and just like, let's start reading here. That's all this does. You can just kind of start where the reading kind of pointer is. You can start it at a different point in the message. But so yeah, that's kind of all you need to know here. And yeah, actually, so I think this is actually where we ended. Yeah, this is where we ended in the first lesson. So that is actually all for today. I think I'm going to stop the recording here, and or if you have any questions before that, I'll stop the recording. We can chat a little bit more later or after that. But
thanks, Justin.
Yeah, this is my goal here. All right, let me stop figure out how to do this. Okay.